Welcome to my mini lecture Tomography 203. The previous video, Tomography 202, showed the simplest ever possible example of pixel-based tomography. We saw there that non-uniqueness and ghosts can cause trouble even in a case of a 2 by 2 pixel grid. In this video, we take a baby step towards more realistic tomography using a 12 by 12 pixel model. Prepare to meet the true nemesis of inverse problems, ill-posedness in the form of almost ghosts. In practical tomography, we would collect X-ray data of a physical object, such as a patient in a hospital. There are no pixels in the real world. However, in this video we work with numerical simulations, so we model the real world with a fine resolution image. Here is our bunny target at resolution 1024 by 1024 pixels. Of course, this is not a tomographic slice, and in practice one would never collect X-ray data of a drawing, but it's cute! Kawaii! We focus here on sparse tomographic data, so we use only 11 directions distributed evenly over 360 degrees. This is very different from the continuous data collection discussed in the Tomography 100 series. Another novelty of the 200 video series over the 100 series is that we model the X-ray detector more carefully. So instead of our simulated detector collecting data at every point of the line, we collect only 21 numbers. This is realistic, as every X-ray camera has just a finite number of pixels. But why 21? Well, I'll explain that in a minute. It just comes from our choice of 12 by 12 target and conventions of the Matlab software. With the finite detector, the data from all 11 directions looks now a bit jagged. In practical tomography, you should of course match your model with the actual number of pixels in your X-ray camera. We want to build a matrix model for our tomography problem, just as we did for the 2 by 2 pixel case in the Tomography 202 video. We choose a 12 by 12 computational grid, as it has few enough pixels to keep our matrices small enough so that they are easy to examine. But 12 by 12 is also fine enough pixelization to illustrate the ill-posedness of our sparse tomographic problem. Now our reconstructions will always have size 12 by 12 pixels. Therefore, the best we can hope for in the reconstruction is to achieve a downsampled version of the original phantom image. Let's see why our simulated detector has to collect exactly 21 data points. That comes from the inner workings of Matlab's radon.m routine. If you use some other simulation software than Matlab, you may arrive at some other number, but anyway it will follow some kind of similar inner logic. Our image grid is square and has an even number of rows. In such case, Matlab puts the center of rotation in the middle of the northwest pixel of the central 2 by 2 pixel cluster. We look at rays at a 45-degree angle, since perpendicular to them there's the maximal origin to corner distance. Rays are added one by one as long as they intersect the grid. Finally, we got 1 plus 10 rays, the last one just outside the grid. We keep all these and add rays to the other side as well. For symmetry's sake, there are 10 rays also on the opposite side. Now the total is 10 plus 1 plus 10 equals 21 rays. We now build a system matrix for our 12 by 12 pixel tomography model. The The first step is to number the unknown X-ray attenuation values inside our 144 pixels. We follow Matlab's convention of column-wise numbering, like this. We have 11 directions and 21 X-rays for each of the directions. Every X-ray corresponds to one row in the matrix. Therefore, our system matrix A has 11 times 21 equals 231 rows. Our unknown image has 144 pixels, so the matrix A has 144 columns. The matrix model now is AX equals M, where X belongs to R144 and M is a vector in R236. We can collect the measurements into a sinogram, similarly to what we did for full data case in the video Tomography 104. There are no ghosts in our tomographic model, since the matrix A does not map any non-zero vector into zero. But there are almost ghosts, which is maybe even worse than just regular ghosts. Let's drop our 12 by 12 bunny image into a vertical vector and multiply with the matrix A. The result can be collected into a sinogram. So far so good. Here is another 12 by 12 pixel image. It looks nothing like the bunny, but its sinogram is very similar to the bunny sinogram. We can even quantify this observation. The difference between the bunny image and the noisy image is 134%, while the sinograms differ only by 0.1%. Here I used a simple norm formula for calculating the root relative square error, RRSE. Here is another example of an almost ghost. And even if we demand non-negativity from the almost ghost, there can still be several times more difference between the images compared to the difference in sinograms. This is called ill-posedness. The previous video, Tomography 202, showed that even in the tiny 2 by 2 pixel grid case, we can have non-uniqueness. This video illustrated ill-posedness with a 12 by 12 pixel grid. Even if we have formal uniqueness in the inverse problem, almost ghosts lead to difficulties in image reconstructions from noisy data. How can we reliably recover two very different objects if their data is almost the same? Stay tuned to the Tomography 200 video series and you'll know. I will show you how to overcome ill-posedness using regularization.